Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering is recurrent neural networks, which is topic number 8 in the list of topics of this course. And the subtopic is C. So the difficulty level is moderate to difficult. That's why it's 8C. And this video and the content is developed using the supplemental website www.easymcq.com/GoGet, which is a personalized learning management system. Now, this is the way the content is delivered in this course. So this is not only the future of content delivery, it is also the present of content delivery, because there are literally 100 million users which are using this approach for online content delivery, for learning, and for getting to know different topics and subjects. And the benefits of this approach is listed in front of you. So the green color link, hyperlink, is the address of the personalized learning management system, and which is developed using the content delivery approach. And the key 6 features are available in the form of 6 videos, which I strongly urge you to view. And the address of these videos is given in blue color. And the beauty of this approach is that it provides basic and advanced text search in the contents of the material. It also supports people who have visual disabilities by setting the font, color, spacing, etc. of the content to view. And it is also optimized for the small screen of smart handheld devices, and you can track your progress also, what you have covered, what you need to cover, and you can also test yourself about the knowledge accumulation, the knowledge assimilation, and identification of weaknesses. So there are two approaches of knowledge transfer. One is the question and answer based approach. The other one is the traditional slide based approach. So in this video, we have adopted both the approaches, and the Q&A approach is proactive, it is adaptable, and it is engaging, and it is also provoking thought, which machines have difficulty in doing. And it also contains the details which are of the traditional approach. So this is a blended approach. This is the best of both techniques. So this is the list of topics which are covered in this course, and we are currently at topic number 8, which is recurrent neural networks. And these are the details of that topic, and these details are in the form of questions and answers, which are concepts. So the easy ones are in yellow color, then the easy to moderate in in green color, then the blue color, and so on. So without further ado, we move on to the details of this lecture. So now we start with section 8C of deep reinforcement learning, recurrent neural networks. So which variables are most difficult to train in the recurrent neural network, and give an example also and why it's difficult. So this is an interesting question and an interesting concept also. So to give you an idea, if you look at this unfolded recurrent neural network, so there are 3 weights, as a matter of fact: U, V, and W. U, V, and W, they are weights. And then of course these weights are of the hidden layer and the output layer and so on. So, and of course we need to take into consideration. Now if we go into a little bit of background, so in RNNs, uh, in the context of deep reinforcement learning, certain variables are inherently more difficult to train, because this is recurrent neural networks and the gradients are propagating through time. Gradient calculation, it is itself a big challenge. There is a whole topic on it. Now we are looking across the gradients across the time. So the recurrent connection weights are the hardest due to repeated multiplications that of course lead to vanishing or exploding gradients. So as I've shown you just now, these weights V, U, and W, they are the hardest to calculate. So then of course are the Bayes terms in the recurrent layer. Although these Bayes terms are additive, but still they suffer when the gradient flow is weak. Okay, and then their effect kind of entangles with the weights. So it's a complicated problem. The input weights kind of struggle when assigning the credit across distant time steps, as the reason being that the gradient signals get diluted through the recurrent chain. Now output weights are comparatively easier to train because their gradient paths are short and they are less affected or impacted by deep recurrence. And finally, the long-term dependencies represent the most challenging requirement. What is that challenging requirement? Training signals over large temporal spans, which of course degrades unless suitable architectural mechanisms are in place that result in stable gradient flow. And we have discussed about four or those architectures. So we move ahead and we start with the these subtopics, so to say, or the bullets. So recurrent connection weights. Now these are used at every step to propagate the hidden state, and their shared influence across time makes them, since they are shared across time, so they are prone to vanishing or exploding gradients during training, which kind of destabilizes the system. And this is very true for long range dependencies. Then we have the recurrent layer biases. So bias in recurrent update acts as constant offset at every time step. Although this is additive, but their effect is modulated through time and is less directly trainable. Why? Because the gradient signals are weakened by the recurrence. So we are trying to solve a challenging problem. Then are the input layer weights. Now these map inputs to the hidden states, and their gradient must flow through recurrent connections to affect the long-term outcomes. But that makes them hard to optimize because of the long term for distant dependencies under the gradient attenuation, as the gradient kind of gets weakened. Okay. Then are the output layer weights. Now these connect hidden state to output. Now with shorter gradient paths, they are less affected by the vanishing or the exploding gradients, and thus they are more straightforward to train more reliably as compared to the recurrent weights, which have to be unfolded in time. And finally, the long-term dependencies. The long-term dependencies. So those they represent relationships across distant time steps. Now training them is difficult because the gradient signals weaken or attenuate or explode over long propagation chains. The solution is using specialized architectures that help maintain these dependencies. So it is challenging. The nutshell or the message to be taken home, that it is challenging. So now we move to the next concept. Now we have discussed the exploding gradient problem in convolutional neural networks. So now we are going to look at the exploding gradient problem in recurrent neural networks, and then how this problem can resolve using clipping. So this is the example which we looked at when we were looking at CNN, and this is the example with clipping. So these are the points which we will be covering in this Q&A. So when and how does the exploding gradient problem arises? It arises in RNN when back propagation over long sequences multiplies the gradients through recurrent weights when they are kind of unfolded. That causes the gradients to grow exponentially. And consequently, this leads to extreme unstable parameter updates, which results in divergence or numerical overflow. So a practical remedy is gradient clipping. As you can see here, this is without clipping and this is with clipping. So that can be either clipping by value, that is bounding each gradient component, or it could be clipping by norm, scaling the entire gradient vector, if its magnitude exceeds a certain threshold to avoid exploding. In deep reinforcement learning, where recurrent models are used over long time spans like in RNN, gradient clipping helps stabilize the training by bounding the updates and preventing runaway divergences. Actually, in practice, clipping by norm is preferred instead of clipping by component, Okay, by threshold, I'm sorry, is why? Because it preserves gradient direction, which makes it standard technique in deep reinforcement learning implementations with recurrent neural networks. So these are the points which basically convey what I just discussed. So we start with the exploding gradient problem for RNN. So this occurs when gradients increase exponentially across many recurrent steps, especially when recurrent weight eigenvalues exceed 1 or unity. And of course, this undermines learning by producing massive and unstable updates, which makes the training unstable. So, what are the consequences of this gradient problem? The consequences of this gradient problem is instead of converging, it leads to diverging weights. It results into numerical overflow like NaN, not a number, or like division by zero or infinity, or it can result in oscillatory loss. Or and of course, when it leads to diverging, it is a failure to converge. So the training becomes unstable and it is often unrecoverable. So that's a big loss. So what happens when we do clipping by value? So what it does that it caps each gradient component individually within a fixed range, say for example between minus c and c. C is the clipping value. And it prevents extreme values, but what can happen that it may distort the gradient direction because of the clipping. So that is not very attractive. Clipping by norm. So what it does is that it scales the entire gradient vector if its norm exceeds the threshold. Now what the benefit is that it preserves the direction while limiting the magnitude instead of clipping by value that that distorts the direction of the gradient. So therefore clipping by norm is a preferred method for stability. And then is the application in deep reinforcement learning. In recurrent neural networks, based components of like recurrent policies and critics and so on. Now clipping bounds updates prevents kind of explosive training, and that ensures stable learning across long temporal dependencies. So, so this is you can see that without clipping, there is that tremendous increase, and clipping contains that enormous increase or unstable learning. Okay, so the details are here, is sufficient details are here for you to understand, and you can also look at the reference for further reading. So now we move to the next concept or Q&A. So how do long short-term memory LSTM improve standard RNNs? Okay. So let me give you a little bit of background. So these are basically this is the RNN and this is the LSTM. We also spoke about a little bit about gate updates. So LSTMs offer several optimization benefits over standard RNN in deep reinforcement learning. So what happens is that their architecture improves the gradient stability, which is not a norm in RNN. So that allows better learning from delayed rewards. We have discussed what is meant by delayed rewards. Now, through memory control gates, they selectively retain or discard past information. What it does is that it improves focus on the relevant features only, because things which are not relevant they are discarded. So in partially observable settings, LSTMs maintain meaningful internal representations. What it does that it enables more informed actions. Okay, more informed actions, and they also enhance the learning efficiency. How? By supporting better credit assignment and by the reduction in the number of updates required. Finally, there's something called as a sequence adaptability that allows agents to operate across variable length episodes without loss of performance. Now, together, these advantages make LSTMs a powerful tool for solving the optimization challenges than standard RNN because they struggle in deep remote learning. So, this is the standard RNN, okay, and you can see that how the input gates work, how the output gates work, and then how the hidden states are handled. So let me explain all of this to you. Okay, let me explain this. So first thing is let's go into more details. So first thing is the gradient stability. So LSTMs overcome the vanishing gradients via controlled memory and gating, which enables them to capture long-term dependencies, okay, which instead of creating a problem, they are useful because they are critical for delayed reward learning in reinforcement learning. Delayed reward, as I spoke with you, like playing chess. And then is the memory control. Then is the memory control. Now, gated memory architectures uh, allows LSTMs to learn what to remember and what to forget. What it does that it enhances the focus on important states or transitions over the period of time. Then is the partial observability. Now LSTMs maintain hidden state over time. What it does that it allows agents to act intelligently even when full environment information isn't observable, which is not an exception, but which is the reality, which is the everyday thing. So learning efficiency, now improved credit assignment and temporal modeling allows LSTM based agents to converge faster with fewer policy updates. Now remember that credit assignment means that how much a parameter or parameters contributed towards the output or the error. So that's the credit assignment. And then finally we go to the uh, sequence adaptability. So what is sequence adaptability? Now LSTMs handle varying episode lengths and irregular sequences. So that improves generalization and that improves stability across diverse and deep reinforcement learning tasks. Let me please clear this. So in the LSTM unit which we are looking at, there are three main gates. So this is a model, and these gates model and regulate the flow of information. For example, there is the forget gate, what to forget, input gate, what to update, and output gate is what to output. Now it has a cell state and it has a hidden state also. Okay, the hidden state, the output at each time step. So at each time step t, the LSTM receives the input vector, the hidden state from the previous time step, the cell state from the previous time step, and for the forget gate decides information to discard from the cell state. So if there is the sigmoid activation, then there are the weights, then there is the bias, and so on. So the input gate itself decides what new information to store in the cell state. All right. So we have a lot of things going on, and then is the output gate decides what to output and so on. So what are the advantages of LSTM? Remembers long-term dependencies, controls memory through gates, and avoids the problem of vanishing gradients. So that's why we have discussed LSTM in this Q&A.